Hi everyone. Hey, so we're pretty much finishing up topic 1. Okay, we were looking at solutions. We finished looking into solutions preparation, solution stoichiometry. Now we're going to move on to something that is definitely related to solutions. But this is not topic 1. If anything, this is actually topic 8. You may be thinking, man, what happened? Are we all of a sudden jumping all the way to topic 8? Well, kind of, because topic 8 is strictly about acid and base chemistry. And if you look at acid and base, they are actually solutions. You know that because when we were doing nomenclature, one thing you learned about in terms of naming acid and base is that they are aqueous in terms of state. Okay? For example, HCl. HCl is a gas, hydrogen chloride. But if HCl is dissolved in water, which becomes aqueous, we don't call that hydrogen chloride. We call that hydrochloric acid because right now, as an aqueous, it would have acidic property rather than gaseous property. All right? So since acid and base is related to solutions, it only makes sense that we talked about this since we're talking about solutions. So I would say 80% of topic 8 will be talked about here, and the remainder we will talk about later in the next semester after talking about equilibrium in topic 7, because I guess it will only make sense to talk about the remainder 20% after we learn about exactly what equilibrium is. All right, so let's talk about acid and base in terms of its physical property. Now, these are simple physical properties that I hope you remember. Okay, so let's take a look at acid first. So if you take a blue litmus paper and you dip it into a solution that is acidic, the litmus paper will turn red. Now, what happens if you take a red litmus paper and put it in acid? What would it become? Well, it will stay red. Okay, so it's not a good idea, I guess, because if you take a red litmus paper and it stays red, yeah, it's acidic, but it can also be neutral. But if you take a blue litmus paper and you stick it into something acidic and it turns red, then you can pretty much bet that it is an acid. All right? Litmus paper is not something that is widely used anymore. A lot of people don't use litmus paper. Okay, but a lot of people still does. I guess school still does because litmus paper is cheap. A lot of times when we want to test to see if something is an acid or a base, we either use pH paper or we use pH probe. The reason for that is that not only does it identify if it's an acid or a base, but it also tells you how acidic something is and how basic something is. Okay? Based on pH scale. So, but I guess these litmus paper is cheap and it is actually the fastest way to test if something is acidic or not. And there's also other things like phenolphthalein, something that you're going to be using when you do acid and base titration later. Okay, phenolphthalein turns pink. Well, it goes from clear to pink if a solution is basic. Okay. All right, so let's continue on with the property of acid and base. So in terms of acid, it turns blue litmus paper red. Another thing is taste. Now, it's not like I'm going to ask you to taste these things or anything, but acid tastes sour. Now you kind of know that. Vinegar is a popular weak acid that people put in their food. I do. I put vinegar in my French fries, believe it or not. Yeah, you'll probably think that, man, Mr. Lung, that is sad. That's sick. But I like vinegar in my fries. Okay. Now, yeah, it tastes sour. Vinegar tastes sour. We all know that. Another proof, it's pretty disgusting proof, is that your stomach acid, which is hydrochloric acid, also tastes sour. You know that because I'm sure there are in some point in life, or probably happened before many times, that you regurgitated. Okay, you felt sick and you vomited. Okay, your vomit tastes sour. That's something I hope you already know, but don't like to experience. Now, one of the things that you should not do if you regurgitate, let's say you felt sick and you're vomiting, don't leave your vomit in your mouth. Why? If you look at the third property here, acid actually corrodes metal. Acid reacts with metal. We know that. Okay, we looked at the reaction before. Like, for example, hydrochloric acid. Hydrochloric acid can react with, let's say, zinc, okay, which is a metal, to produce zinc chloride and hydrogen gas. Okay, so it corrodes metal. Why don't you want to put or leave vomit in your mouth? Well, the hydrochloric acid can certainly react with the calcium. Where's calcium? In your teeth. You can try it if you like. Okay, leave vomit in your mouth for a long period of time. You'll notice that your teeth gets very tender. Not a good thing. Not a good thing at all. Well, I guess if you were to vomit, make sure you vomit it out or swallow it back. I don't know. All right. There's another chemical property here, so not just physical property, but acid neutralizes base. Okay? And we will definitely see that when we do our titration, and that is something that you already know because there's a reaction, okay, that we have looked at already, where we take an acid, okay, and we react it with a base, and this is neutralization because it creates water and a salt. Okay, so again, something that we've seen before. So let's move on to the other side. Let's take a look at base. Okay, now back to litmus paper. There are blue litmus paper, of course, that will turn red if you dip it into acid. But of course, there's always red litmus paper that turns blue if it makes contact with a base. Right? Now, about taste. In terms of taste, base are bitter in nature. Okay? Now, I wouldn't say prove it. I wouldn't ask you to prove it or anything, but it is. Now, there's a feel to base. Unlike acid, which you shouldn't be touching, base you shouldn't touch neither. But if you were, because it accidentally fall on you, like certain washing detergent, they feel slippery. Okay? Now, if acid neutralizes base, it makes sense, of course, base neutralizes acid. Okay? Now, those are, of course, some basic properties about acid and base. Now is the juicy stuff. Now is about the theory behind acid and base. Now, what makes an acid and what makes base a base? Well, there's a couple of theory. Okay? There's a couple of theory. The first one is more like a more basic theory behind this, known as the Arrhenius theory. Arrhenius. Okay? Obviously, it's some dude who worked with acid and base and kind of give you a little, idea of what makes an acid. What does it do in a solution that is different from its gas counterpart? Okay, so this dude right here, Arrhenius, discovered all of this. Now let's take a look at what he looks like. I actually have a picture of him, believe it or not. Here, there we go. This handsome man right here, his name is Arrhenius. Okay, if anything, he looks like a wrestler. He reminds me of a wrestler. That's what he does. Give him a bandana. Give him a bigger stash. And he looks just like a wrestler. Anyway, that's Arrhenius. Okay? And Arrhenius says, in his theory, that an acid is something that has hydrogen in it. That when this acid is put in water, it makes H plus and Cl minus. So that's what Arrhenius says. So let me draw a little picture right here. Now you might have already seen this picture before, but this is HCl in its Lewis structure. Okay? And this is a gas. And if you, let's say, obviously this is a hypothetical diagram, that if you take HCl and you dissolve it in water, what happened is that chlorine will take both of these electrons that are being shared. Chlorine will take them both. Chlorine says, I don't want to share electrons with you anymore, H. Water is here. I want to take all the electrons and I want to be chlorine minus. I am now an ion. Okay? Now, what about H? Poor H. Poor H is now electronless. And he's now an H plus. Okay? This situation right here is an aqueous situation because HCl is no longer together. HCl is actually separated into its ions, so it is now an aqueous. Now, this is something that we've seen before with those ionic compounds like NaCl, KF, FeO. Those are all ionic compounds. And if they are soluble in water, they are separated when they're in aqueous state. Okay? The difference here is that HCl is a covalent compound. You see the sharing right here? But it kind of acts like an ionic compound when it is immersed in water. So that's what Arrhenius says. Arrhenius says, that dude who looks like a wrestler, says if you put HCl or any other acid, okay, it could be sulfuric acid, nitric acid, acetic acid, you put that in water, okay, you get H's, H plus. That's what he says. Well, what about base then? Well, for base, like for example, NaOH, sodium hydroxide. If you put that in water, it will break apart too. You'll get Na plus and OH minus. Let's draw that too. Why not? Okay. Now, NaOH is an ionic compound, that's for sure. You have Na plus, okay, ionically bonded to OH minus. OH obviously is a polyatomic ion. So if you were to immerse this in water, like all soluble ionic compound, they will separate into Na plus and OH minus. Okay? Of course, here is your aqueous. So it's very simple. That's what Arrhenius have discovered. So in terms of his conclusion, okay, which is stated right here, in page 184 in your course pack, hopefully you guys are writing this with us, that although successful in this theory, okay, where acid, when in water, will make lots of H plus, and bases in water makes lots of OH minus, there are some problems though. And these problem is not something that Arrhenius can solve. He will have to wait for a while for somebody, I guess, smarter to discover what really happens here. Okay, so let's take a look at what's happening. So what we know right now is that acid make lots of H plus, bases make lots of OH minus, but H plus is actually very unstable. It really have no business being there in a solution as a standalone. Okay? Meaning that H plus don't exist. If it does, it doesn't exist for a long time. It will try to find something to react with. So, seeing the fact that there's lots of H plus in a solution of HCl is actually not entirely correct. Okay? So, this is not something Arrhenius have discovered. But it's obviously something that you will learn very soon, is that H plus, because it's so unstable, it will actually react with water to form H3O plus. Now, I will show you exactly how that works later when we look at the next theory. Okay? And that is something that Arrhenius couldn't prove. Okay, he wasn't able to actually see what the fate of H plus is going to be. Not until later on, people understand that, oh yeah, I know what happened to H plus. H plus will grab water and say, hey water, I am a very unstable dude. Can I hook up with y'all? Can we become H3O plus? And of course the answer is yes, because hydronium right here is stable. It can exist. Now somebody told Arrhenius, you said that all bases creates OH minus. Well, I have this base right here called NH3, ammonia. How does ammonia be basic when it doesn't have an oxygen to create OH with? Oh, that's obviously a huge problem. Because if you take a pH meter and you put it in a solution of ammonia, it is going to tell you, oh yeah, it's above 7, it is basic. You put a red litmus paper in a solution of ammonia, it will turn blue. Okay? So ammonia obviously have all the basic property. But how is it going to make OH when this guy doesn't have an O? So that kind of puzzled Arrhenius. So it will actually take a while for somebody else to actually prove that NH3 is a base. It will take a while for somebody to prove that H plus reacts with water to make H3O. Now, obviously for us, it's not going to take that long. It will be right now. Because what we have in the second theory is this is the Bronsted-Louie theory. Okay? Now I showed you what Arrhenius looked like. Let's take a look at what Louie looks like. I have a picture right here. I have pictures for everything. There's Arrhenius. Okay? There is right here. There's Louie. I guess this is the only Louie that we care about. Okay? And it's obviously not him. He's probably the best Toronto Raptor ever, in my opinion. I'm sure right now, Serge Ibaka, Kawhi Leonard is probably thinking, man, I wish I was playing with Kyle Lowry. Anyway. Oh, what happened here? There. This is the Lowry that we're talking about. This Lowry right here. He's no baller. I'm sure he's not very good. But what he is good at is telling you exactly how acid and base works. And here his BFF, Bronsted. Okay? Alright? So, what did they say? What makes them so famous that we're going to talk about them? Well, basically, they picked up where Arrhenius left off. Okay? Arrhenius was unable to prove this. But Bronsted and Lowry is going to. And this is what Bronsted and Lowry said. And this is something that you have to know. An acid, by definition, is something that have the ability to give up hydrogen ion, which he calls proton. Now, the reason why it's called proton is because H plus only has one proton, no neutrons, no electrons. So, hey, if you only have one proton, let me just call you a proton. Okay? So, all acid is considered to be called a proton donor, because that's exactly what an acid does when it is immersed in water. It donates H's, like we saw right here. Okay? When HCl is dropped in water, it makes H+. It donates H+. Okay? That's why it's called proton donor. Now, a base is known as a proton acceptor. Notice Bronsted and Lowry did not say anything about OH minus. Right? Take a look at his sentence. His theory didn't say anything about hydroxide. His theory says a base is something that accepts proton. My goodness. What does that mean? Now, I'm going to give you some example of bases right here. Okay, I want you to write this down. And these are popular base that you need to know. Okay, basically things that are metal oxides in nature, like calcium oxide, sodium oxide, iron oxides. These are base. Okay, we saw ammonia can also be a base. Both metal oxides and ammonia doesn't have hydroxides in it. So Arrhenius' theory about OH being an example of base, and only example of base, is actually not true. Because metal oxides are basic too. Ammonia, we saw, is basic. Okay? And obviously we know that metal hydroxides are also a base. Okay? Now, there's a word that here I want you guys to know about metal oxides, okay? So metal oxides that are soluble, as in soluble in water, has a special name called alkalis. Okay? Usually, okay, group 1 alkaline metal hydroxides are alkalis, like sodium hydroxide, potassium hydroxide. Okay, they're alkalis because they're soluble in water. So some, I guess, terminologies that you have to keep in mind. So let's do some drawings again. Let's go to the next page. Okay. Oh, one page too many. So here's an example right here. HCl plus water. Okay, let's draw. I have a beaker right here. And here's my HCl. Let's make this big. Okay, and I'm going to drop HCl in water. Here's water. Now, one thing is not wrong about Arrhenius is this. He's not wrong about if you take HCl and you put it in water, you will get a separation. You will get Cl minus, and you're going to get H plus. He's not wrong about that. In fact, he's very right about that. Okay? But what he doesn't know, as we mentioned, is that H plus is very unstable. Cannot exist in a solution like this. He has to be stabilized. Who's here to stabilize H plus? Well, H2O right here is going to stabilize H plus. H2O will say, man, poor H plus. Poor you, the fact that you're standing right here all unstable and stuff. I'm gonna take you in. Just like these H's right here who are very comfortable with me. I'm gonna take you in. I'm gonna draw you in by sharing both of these electrons with you. As a result, we become this right here. Okay? Let's call us hydronium ion. Okay? Remember? Dative bond, coordinate, covalent bond, whatever you like to call it. That's exactly what happens to H plus. So the fate of a proton is that it is being taken in by water to form a dative bond to create something called hydronium. Okay? To call something hydronium. Because only hydronium would exist because it's stable enough to do so. Now, mathematically, this is something that I want you to write down, that the concentration of H plus is always equal to the concentration of H3O plus. Okay? The two, in terms of numbers, is always equal. So you'll see mathematical formula where they use this instead of this, because I guess it's easier to write. So what you need to know is that since they're equal, they can be used interchangeably, quantitatively. But in reality, in a solution, only this exists. All right? So if you look at how to predict the reaction here, that if you take HCl and you react it with water, what you're going to get is you're going to get H3O plus and Cl minus. Okay, don't forget about this guy. He's going to stay there. He's there. Okay. So here's your what we call proton donor that Bronsted and Louie is talking about. Okay, this is definitely a proton donor. Donates H to H2O. Let me say that one more time. Acid donates H to H2O. Proton donor. Here's a base. Bronsted says a base is a proton acceptor. Okay. Because this is actually the best way to talk about bases like this. Okay, let's draw this. Let's draw. Here's another beaker right here. Notice that I'm using blue for base, red for acid. Here's water. Proton acceptor. Here's my ammonia. Ammonia is a covalently bonded neutral molecule. Okay? If you were to drop that in water, what you're going to see is this. No separation here. But NH3 in its lone pair is going to somehow say, hey, hydrogen, leave water. Leave water. Come to me. Because this lone pair right here is better. You be better off staying with us rather than staying with him. Oh my gosh. He pretty much just stole hydrogen off of water. So what do you get? Well, what do you get here is that you'll have, right now, not NH3, but NH4. And this, right here, has a positive charge in nature. Okay? Because of formal charge. Wow. So what happens to water then? Well, it seems like water is no longer H2O, which is no longer water. What you have right here is OH. Wait. Arrhenius, back here, says bases have the ability to produce hydroxides. And we saw how NaOH can easily produce hydroxide by dissociating. Arrhenius couldn't figure out why NH3 is a base, because NH3 do not dissociate, nor do it have oxygen to make hydroxide. But now we know, oh my gosh, now we know. It's because NH3 have the ability to take an H off of water. This H right here didn't even want to take those 2 electrons. This H right here says, you know what, water? I'm leaving. I'm getting my bags out of here. Actually, I'm not even going to take my bags. You can keep my bags. Keep my bags. I'm going to take myself out of here. I'm going to hook up with ammonia and become ammonium. I want to become ammonium. The fate of water is the hydroxide that Arrhenius was talking about. So NH3 do produce hydroxide. But the hydroxide wasn't part of ammonia. It was actually water. Pretty sick, huh? So to finish off this reaction, H2O plus NH3 will give you, oops, why did I put, will give you NH4 plus and OH minus. Just like how my drawings are proving the fact. Now, there's actually a problem with this arrow though. Okay, there's actually a problem with this arrow. This reaction right here is not a unidirectional reaction. It's actually an equilibrium reaction. But that's not something you need to know right now. Okay? Maybe later. Maybe later. All right, let's fill in those words. So in reaction A right here, H2O accepted a proton from HCl because HCl is acting water in this case. Sorry, water is accepting the proton from HCl. So if you think about it, water is playing a certain role. Okay? And let's take a look at water for a sec before we actually fill in these empty words. Because you can see that water appeared in 2 places. Okay, right there and right there. So if you look at this reaction right here. We know that HCl is an acid because it donates proton. But if you take a look at water, water actually is acting as a base. Because what did Brownstedt, Louie said about base? Yeah, base is a proton acceptor, right? Isn't he acting as a proton acceptor by accepting this proton? That's strange, but that's true. So let's write this down. In A, water accepts a proton from HCl. So it acts as a base. So water is acting like a base. Oh, okay. While in B, so if you look at reaction B right here, water in this case is donating an H. Because NH3 is a base. A base is a proton acceptor. So NH3 is accepting a proton to become NH4. So yeah, he's a legit base because he's a proton acceptor. But if you look at water in this case, water is actually a proton donor. So, in B, water is actually acting like an acid. So what is water? We know that if you put a pH paper in water, water is neutral. But if you look at the reaction here, in this case, water is acting like a base. In this case, water is acting like an acid. Wow. What do we call people like that? Well, water is what we call amphiprotic. What that means is that this chemical right here can act as a base or an acid depending on who he is reacting with. So if water is reacting with an acid, then I'm going to act like a base. If water is reacting with a base, then I will act like an acid. So that's what amphiprotic means. So all Bronsted acid in this formula will contain hydrogen in it. And hydrogen is obviously the key. All right. So hopefully you kind of understand the whole idea of proton donor and proton acceptor. Okay, where water can act as a proton donor and water can act as a proton acceptor depending on who he's reacting with. All right. So that's the chemistry behind acid and base. Okay. Now, I want to talk about one more thing before we call it for the day. And let's write it down here. Okay. That acid can be what we call monoprotic, diprotic, or triprotic, depending on what acid you are talking about. Okay, we know that mono means 1, di means 2, and tri means 3. Okay, protic means H. So acid can be monoprotic, meaning that this acid will have 1 H. Like for example, HCl. Di means 2. Okay, so you're looking at acid that has 2 hydrogen involved. Example, H2SO4. Okay, an example of an acid that is triprotic is this one right here, H3PO4, phosphoric acid. Now, they should have AQ, but obviously I'm not putting the AQ down. Now, let's take a look at an example right here, okay, for monoprotic. So HCl is monoprotic. The reason is very simple, is because HCl in solution dissociate to give you H plus and Cl minus. Okay, that's what makes a monoprotic and that's actually very simple to understand. However, diprotic, you will understand more fully later on in the next semester. Okay? Because H2SO4 will go through a series of reactions if it wants to. Now, sulfuric acid is a strong acid. Now, we'll talk about strong and weak acid later on, but H2SO4 is an acid for now, of course, and it will too dissociate to give you H plus and HSO4 minus. Okay? If you remember, this is the bisulfate or hydrogen sulfate anion. Now, the thing is this though, it doesn't actually, it just stops here. For diprotic acid, if necessary, meaning that it depends on the situation, HSO4 can ionize. Again, the word ionize means to create ions, where HSO4 can donate another H plus. As a result, your bisulfate will turn into just a sulfate. So H2SO4 actually has the ability to donate two H's, hence diprotic. This is what it usually does. The second H plus, only if it's necessary. You'll see what this means later on in the next semester. I'm going to draw something that you guys have never seen yet. And notice that my arrow looks a little messed up, right? It doesn't look like this. It's because I purposely drawn it like this. You're going to draw this. Now what that means, this is called an equilibrium arrow. What this is that this reaction doesn't only go forward, but it has the ability to go backwards. If necessary, right? It's all dependent on something known as K value. And we will see that later on. Okay? Anyway, that's it, I guess, for today. Okay? So the summary for what we learned today is that we learned about how acid and base have different properties. You need to know what their properties are and their definition. Okay, their idea, the Arrhenius theory, the Bronsted-Louie theory. Okay, what really is an acid? Well, it's a proton donor. What's really a base? Well, it's a proton acceptor. All right, let's call it a day now. Bye now. See you guys later.